Welcome back, everyone. Next speaker is Anna Felikson, who's going to tell us about finite mutation type in presence of coefficients.
Okay, so first of all, thank you for coming, and thank you to all the organizers who let me speak here, and especially to the organizers of the program who made the whole big thing, and it's so nice to be here. I mean, it's probably the main message of my talk. For everything else, I mean, since I still have 30 minutes, I will probably speak about something else, but the main point is really this. Yeah, okay, so I'm going to speak about a joint work with Pavel, which recently appeared on arXiv. So what are our settings? Let's be a quiver without loops, without two cycles, or everything as usual, and even everything is integer today for a change. So usual mutation rules, and usual question when the quiver is mutation finite. And of course, we know the answer since many years, so I am showing it here, but it will also appear on the screen in a couple of minutes. I mean, we know the classification, but as Sergey Fomin once rightfully noticed to us on the conference in Michigan, that we do know the answer, but only when there are no frozen variables. And if I will start to add some frozen variables to the pictures, I don't know what will happen. So the question for today is when my quiver is mutation finite, given that my quiver now has some frozen variables. Okay. Let me specify the things. So it's exactly what I'm going to say next. So by frozen variables, I assume something which I don't want to mutate in, and there will be no errors between frozen variables because I don't mutate in them. And in matrix notation, we can always think that we have a big black quiver Q, and we add several frozen vertices. Each frozen vertex corresponds to some line in the extended exchange matrix. And these lines are changing by usual rules. Now, since so two observations. One observation is that if the big quiver with frozen variables is mutation finite, then at least the unfrozen part should be mutation finite. So what we know for sure that this black unfrozen part, it should be one of things which we already know. We just don't know what we want to add to them. And the second observation is that since my frozen variables don't interact, there are no errors between them. Since they don't interact, we know that it is enough to look at one frozen variable. And then if we can add this frozen vertex, then we can do add them independently. So is it clear? Yeah. Okay. So these two observations bring me to the following notation and to the following reformulation of the question. So I will omit double indices. I will just look at one variable with indices b1, bn. So let me copy the notation here, just for later reference. Again, I'm not drawing anything new on the board. I just make a copy of what is already on the screen. And while I'm making this copy, you may observe that we made an unlucky choice in the very beginning. So it's not the standard direction of the arrows to the frozen variables, but we decided not to recompute everything and just keep this notation. So I mean, that it's not the same. So and I will look at the vector b1 bn 1 2 n, and I will say that this vector is admissible if the quiver together with this frozen variable is mutation finite. So in this terminology, my task is to describe all admissible vectors for every quiver, but also we know that it is enough to look at mutation finite ones. Okay, so any questions? No. Okay, so this is my aim, and I need to say that the first step in this direction was done by Fomin and Zelvinsky in cluster algebra 4, because if the quiver is of finite type, then you can add any coefficient, so you can take any vector and it will be admissible. They also observed and conjectured that this only happens in the finite type. If you have some quiver and you can add any coefficients to it and it is still mutation finite, then your quiver was of finite type. The conjecture was later shown by Ahmed Sevan. He also showed that you don't need to choose to look at all possible coefficients. It is because it is enough to look at principal ones. This is what we know about finite type. And this also shows that when we leave finite type, we need to do something. We need to find some conditions or to do some work. And to do this work, we will use the classification. I mean, this classifications, it says that a quiver is mutation finite if it is either coming from surface. We had a lot about quivers from surfaces today already, or if it is of rank 2, or if it is one of 11 exceptional mutation classes. Now we are going to we are really going to start with quivers from surfaces, but then everything else will be more dependent on the type, like whether your quiver is finite or affine or everything else. And what we know by now, we know that for finite type, sorry, I lost my green chalk, but yeah, here it is again. For all finite type, we know the answer. You can take any possible, any choice of coefficient vector, and it will be admissible. Yeah, and I also want to say that we will do the rank 2 quivers together with everything else. We are not going to consider them separately. So, okay, thank you. Yeah. Sorry, I do have arrows. I was just lazy to put all of them here, but yeah, since the cyclic, you can take any orientation, but for later, the orientation, like the bipartite orientation, will be most useful. Okay. So the first step in this plan is to look at the surfaces. So let's consider a surface. Again, exactly the same setting as in the talks before. So we build a quiver from it, and a flip of triangulation corresponds to mutation in our cluster algebra. Now, we are interested in coefficients. So what are the coefficients in these settings? The coefficients, as we know from Femin-Thurston, they correspond to laminations on the same surface as the triangulation. And what is the lamination? It is a set of non-intersecting curves where we allow closed curves or curves starting from one boundary component and going to another boundary component, or to the same boundary component, or it can spiral into a puncture in one of two directions, something like this. What we don't allow, we don't allow curves which can be contracted like this one, or contracted to a point, or contracted to a boundary point, or if they the two ends spiral into one and the same puncture in the same direction, we are not allowing this to be a trivial curve. So if we have some lamination like this on the same surface as the triangulation is lying, then we use shared coordinates as shown on the board. When the lamination crosses an arc in one way, we say +1, in the other way we say -1. So for example, here, if I look at arc gamma 1, I see two laminations crossing in negative direction. I write -2 here, and for arc 2, I see one lamination crossing in positive direction. I write +1 here. I completely ignore this bit because it is something very local near this point. And then I will write the vector 2 -2. So my vector, since I had this unlucky choice, my vector is negative shared coordinate. Yeah, okay. And the good thing about these laminations is that the shared coordinate make the bijection between laminations and the n. So we get all possible coefficients this way. And also another thing is that the vector of shared coordinates is mutated in the same way as this coefficient vector, so we can really use them to observe what's going on. So now I think we are prepared to state the theorem for surfaces. And I state that given a quiver from triangulated surface, then any admissible vector for this quiver will correspond to some peripheral lamination, where by peripheral lamination I mean some any lamination which can be either top to the boundary. Like I can, my blue curves here can be pushed to the boundary so that the surface is free. And I claim that admissible vectors are in one-to-one correspondence to such lamination. Now, maybe briefly, why do I claim this? So what are these peripheral laminations at all? So the peripheral laminations are exactly the ones which are preserved by all Dehn twists. So luckily we already explained what are the Dehn twists, and if I do a Dehn twist, I change my triangulation in a controllable way, and I keep the elimination intact. And I'm trying to see what kind of intersections my new triangulation has with my old lamination. It's a little bit difficult to keep track in this way, but let me take the opposite then twist inverse, so that I keep triangulation intact and lamination changed, and then you will see that I have the same triangulation, but also the same lamination, because I did not change anything, because my lamination was peripheral. So whatever closed curve I take, and if I start to twist around that, it will not change anything in this picture, and will produce the same vector of coefficients. So if I will try to look at a little bit bigger picture, I have my quiver Q, and I have my exchange graph, and the same quiver appears from time to time on it. But every time from one to another, I can go by a composition of then twist, because then twist generate mapping class group of the surface. And also, if I will take some point which is not the image of this quiver, which is some other quiver, then since my quiver was mutation finite, there is some universal number n such that a quiver like Q will appear in at most n steps, which means that going from Q to arbitrary point, I will not be able to spoil my coefficients too much. So I have only finitely many ways to spoil my point. Okay, so any questions so far? So this tells me that that for surfaces I get peripheral laminations. Let me try some example of that. So here is a affine A1 with two arcs on the annulus. What will be the vector? There is just one peripheral lamination, because I am unable to draw anything else. So anything on the with ends on the boundary is forbidden, because there is just one marked point on the boundary. So the only peripheral lamination is the closed curve, and I can just look how it crosses my curves 1 and 2, and it gives +1 -1, which translates as the opposite. And then what do I know? I know that I have -1 arrow coming to vertex 1, and 1 arrow outgoing. But of course, I can have several copies of this curve. So the real condition is that I have the same number of arrows coming to one and outgoing of the another. And this condition I will call annulus property, because it's something I have on the annulus. Now, notice that annulus is already something affine, so I change the title. It is already. Yeah, I mean, it seems like I'm cheating a little bit. I just changed the title, but actually I did almost all work for affine, because it is almost everything which I will need to check. So the statement is that if I have a quiver or affine quiver containing a double arrow, then the only thing I need to check for my vector B is whether it satisfies this annulus property. If it does not satisfy, then clearly it's not mutation finite because of the annulus. And if it does satisfy, then miraculously it is enough. You don't need to check anything else. Now, this condition of having a double arrow, it's, I mean, if you will look here, it seems that it's sort of a strong condition because they don't. But but in reality, every affine mutation class contains at least one quiver with double arrow. So something like this. in the same mutation class. And this allows us to find a representative in every mutation class where we really can say which vectors are admissible, and if we have a need to go to another set, we just need to mutate and check. Now, maybe a couple of words about the proof here. The idea is to use these good representatives and then to refer to very recent work by Kaufman and Greenberg from the summer, where they compute cluster modular group. They compute cluster modular group and just give precise generators of that. So here, shown here. And it turns out that these generators, okay, in our surface case, remember we said the generators are don't twist and they just keep everything intact. So these generators does not keep everything intact. They change something, but in a very controllable way. You can see that what they change, it's sort of finite, and when you, for every generator, and then you can control them and see that in total this is still finite. So this is the plan, and this is the answer for fine. So you just need to satisfy anomalous property, and then you are done. Okay, so the next thing we need to check is everything else. And this everything else is sort of short because there are no admissible vectors at all for everything else. And the reason for that, I mean, anomalous property is responsible again, because we take, the idea is that we take some quiver and we say, suppose anomalous property was satisfied. And then we construct some mutation, some easy mutation sequence, which takes actually our quiver to the opposite quiver. And then there should be a new version of anomalous property, but if the first one was satisfied, the second will not be. So it takes a little bit of computation to show this. It's not completely clear from advance, and the computation actually is not very nice. Like it's nice in E6, it's still okay in E7. For E8, it's long, but it is yeah, it works. So I mean, we sort of filled everything. Maybe I could even finish here, but I still have several minutes. Let me say some more words about the surfaces, because so far the result was that I should have peripheral lamination. But if you will give me a vector and the surface and the quiver from triangulation, I'm not immediately able to tell you whether it is from peripheral lamination or from something else. I mean, there is an algorithm how you can reconstruct, but let me just give you another way to check. So for this, let me consider a specific triangulation, like nested triangulation, where I first have all holes, then all handles, and then all punctures, and all they sit one inside another. And I can construct a quiver for that. It is very, again, it's easy to control. You have just a chain of things and of different features. And if I do this, then my theorem of about peripheral laminations will translate as follows. So the vector will be admissible if it does not connect to the red part of quiver at all. It can connect to the green part of quiver, but it should respect the anomalous property for this part. And this part is responsible for these inner boundaries. But of course, there should be something like this also for the outer boundaries, and I don't see the good anomalous for it. And that's why I need to put a little bit different condition. So I mean, morally, it also says that the anomalous property works also for this outer boundary. But since there is no separate tunnels there, it looks differently. Yeah. So now if you have a quiver from triangulation, then I will propose you to mutate it to this one and check. I mean, it's still not a good recipe, because when you will mutate, you will spoil your coefficients a lot. But at least there is one seed where you can check. Okay. Now, a couple of words about skew symmetrizable case. You can do the same in the skew symmetrizable case, and you will get more or less the same answer. So in skew symmetrizable case, we also have, the classification, and we can have the same story of finite, affine, everything else. And the only difference is that we will need to speak about orbifolds with, in place of surfaces, and we will use diagrams in place of quivers. And analogous property will get some weights in it, namely, if you have a diagram, not a quiver, but a diagram with an arrow of weight 2, or of weight 4, which correspond to a quiver with an arrow of 8, 2, then we will have these little weights in the analogous property, which translates something like that. And finally, if you don't want to redo all the computations, you also can use unfoldings, because luckily our sequence of mutations, which were considered for, I mean, all sequences of mutations which were considered, they work for unfolding. So they're, yeah. And yeah, I think this is basically what I wanted to say. But the main point is, thank you to the organizers. I mean, it's really brilliant what they did. Thank you.
Questions for Anna?
Can I ask a question?
Sure.
Yeah. So can we restate your main result in the following uniform form, that a vector is admissible if and only if for all quivers mutation equivalent to Q, this vector satisfies the analogous property. And of course, if Q, if the quiver doesn't contain double errors, then this is automatic. So is this criterion correct, or did I misunderstand something?
I think you are completely correct, yes, because for finite type, you will not see any double errors at all. For affine type, as soon as you see a double error, you need to satisfy a condition. And if you satisfied it in one seed, then you will satisfy it everywhere. And in everything else, you just cannot satisfy it in two seeds. So yes, it's a really good reformulation. Thank you.
And is the same thing true in the skew symmetrizable case as well?
Yes, yes, the same, absolutely the same. Yes.
Thank you.
Thank you.
Other questions? Okay, doesn't seem to be the case. So let's thank Anna again.